Ladies and gentlemen, we're going to talk about basicity. How basic is a substance? What number did you learn for the acidity of an amine when it's the conjugate acid? R prime, R double prime. What's the pKa? You're supposed to know that one. 10. 40 is the pKa of an amine, which is not normally thought of as an acid. Well, 40 says it's not normally thought of as an acid. It's very hard to take the H off of an amine, but, you know, we're making these products from amines. Rn, R prime, R double prime, and you add H plus. And you get this. Okay, 10. So we're talking about how basic these amines are. Okay? And what's a better pKb? 4.7 or, let's see, 9.4. Reminder, these are pKbs in this column, and this is the pKa of the conjugate acid. These are the conjugate acids here. Conj acids are up here, just like this column says here. Okay, so which one's a better base, a 4.7 or a 9.4? Now, the lower the number, the stronger the species. Whether you're talking pKa's, where the lower the pKa, the stronger the acid. The lower the pKb, the stronger the base. That's all low numbers mean with the pK. Stronger, lower. So, and this is the 10 that we learned about the pKa. So this is the one we were learning. If you average all these, they're real close to 10, aren't they? So don't memorize these new numbers. Please don't. But please memorize that the secondary amine is a slightly better base than the other three. The other three being tertiary, primary, and I guess you'd say zero dairy. Like an ammonia is like a zero dairy amine. It's not an amine, it doesn't have carbon. But it behaves like an amine. So, of the guys on this page so far, these are the best bases. And the best is secondary. We'll talk about why when we answer the question. It's in the textbook. Moving on. Of these three, which one is the best? The 7. So imidazoles are slightly better bases than pyridine and aniline. Okay? So if you have to put them in order, these are nowhere near as good as any of these. Important message 1, this number and these 3 numbers are nowhere near as good as these numbers. So they're in a second category, second tier. And you got to know the order of imidazole, followed by pyridine, followed by aniline. Aniline's not a very good base. Okay. So do we have enough to at least get some kind of rough order down here? There's something that's not up here, but I'm going to put it here. This is pyrrole. Pyrrole is not there. Why is it not on this list of bases? Pyrrole is a terrible base. Why? This lone pair is necessary for what phenomenon that chapter 21 was devoted almost exclusively to? Lone pair needed for, I need one word. If you don't have that lone pair, this word can't happen. Aromaticity. I'll give you partial credit for resonance. I'll give you full credit for the special kind of resonance that's going around in a circle with the right number of pi electrons and the right atoms with the right hybridization. Yeah, you said it. She said aromaticity. And if you use that lone pair for anything else, you've ruined aromaticity. That molecule has become, no, it never became that. It said, I don't want to become that. I like being aromatic. Don't use my lone pair for anything else. Thank you. Very effusive molecule. Okay, so do you see any paroles on the page? Number one was a parole. It's the worst. Okay, number one is the worst. And your explanation is conj base is no longer aromatic. Conj base. This is the base. Conj acid. I'm so used to doing explanations based on the stability of the conjugate base for acid that I forgot we're talking about bases. You better be talking about stability of the conjugate acid. Conj acid is no longer aromatic. That is a travesty. Shame. It's a mockery. A Travisha mockery. I stole that from a movie somewhere. Okay. Conjugate acid no longer aromatic. Now, are there any aliphatic amines? These are all aliphatic over here. Those are all sp3 carbons attached, right? Because those are the best category. I see two aliphatics, don't you? Give me some Roman numerals. 4 and 6 are both aliphatic. Which one's secondary? Because it'll be a little better. 6. So aliphatic, aliphatic, and aliphatic. Now aliphatic primary is not going to be as good as aliphatic secondary for reasons we're about to discuss. We're going to talk about stability of these two conjugate acids. And it's here. Oops, I dropped the ball on that one. Here we go. There we go. Now, I think you can understand why the cation to the right is more stable than the cation to the left. This one more stable than this based on a concept you already know. More hyperconjugation. Isn't that what's one factor that stabilizes carbocations? How many carbons you attach to them? Works for nitrogen cation too. More hyperconjugation stabilizes this acid. 2 H's for, there's another thing that stabilizes this, and it's based on the fact that you were going to mention something here, right? This two, what's going on? That's not the conjugate acid. This is just a unicorn. Yeah, we don't like unicorns. I mean, I love unicorns, but they don't belong in this course. Sorry. And I noticed because I'm about to talk about 3 H's for, I'm just going to remind you. The experiment where they tested pKa's was the reaction of an acid with water. Water being the acid and the solvent. Water can stabilize certain molecules, especially those that can hydrogen bond like water can. Which of those two ammonium ions can hydrogen bond to a greater extent? The one on the left or the one on the right? Which of these two ammonium ions can stabilize by hydrogen bonding? Left. 3 H's for H bonding. That's better. And 2 H's for H bonding, not quite as good. So we're knowing that hyperconjugation helped the cation to the right, but hydrogen bonding helped the cation to the left. A tertiary amine would have only a little hydrogen bonding because then it gets 1 H, right? So it would have the worst hydrogen bonding, but the best hyperconjugation. These factors are almost equal. Almost. But not quite. Secondary's got the best combination of the two factors. It's got a medium amount of hyperconjugation and a medium amount of hydrogen bonding. That's the best combination. So you need to say that. Secondary amines have the best. So don't write down everything I said. Write this down. Secondary amines, ammoniums, sorry, we're talking about the conjugate acids, have the best combination of H bonding and hyperconjugation.
So the primary and the tertiary would be
primary and tertiary roughly equal, all other factors being considered. Secondary is always the best by a slight amount. Okay? So that's going to put Roman numeral VI at the end. And the close one is IV. And then we get into the ones with the aromatics. Sorry, say again. She likes the imidazoles for being third best, and that's good because after you get finished with the aliphatics, you're going to go to imidazoles, right? Okay, good. And that's an imidazole too. And I want to point out probably the most important thing about imidazole, and it's related to what you talked about right over here, with parole being terrible, because this lone pair is needed for aromaticity. Tell me which lone pair here you're going to use as a base so that you don't ruin aromaticity. Do not pick the one where the lone pair is on the nitrogen. That's the worst lone pair to pick. I'm saying do not pick this lone pair. Pick this lone pair because that nitrogen's already involved with resonance with the pi bond. So I do not mind if you put the H there. So do not use that top lone pair. I am going to make it very clear that this thing becomes this thing. I cannot emphasize enough the importance of this fact. Imidazole and its conjugate acid are the most common acid-base pair in biochemical reactions catalyzed by enzymes. So you better be learning about imidazole. Its pKa being, pKb being near 7 and pKa near 7 means there's substantial amounts of both available under physiological conditions. What is the pH at physiological conditions? 7.4, which means if you need an acid-base pair, you've got a lot of imidazole and its conjugate acid available because the number's real close to 7 to start with. Okay, that's one reason it's the most common acid-base pair in catalysis in biochemistry. Please take this seriously, okay? Imidazole, it's found in the amino acid called histidine. Have you heard of histidine? It's got that ring in it, right there, okay? And yeah. So I like number 2 for here, and she likes 3. The question is, if I put the 2 here, and it's in green, should it be 2? I got 2 2s. Which one of those twos needs to be a 3? That's the question now. She likes the one on the left because she thinks fluorine destabilizes a plus charge on nitrogen, and I agree with her 100%. It's good, and you should say that. You say fluorine decreases stability. Here's what I'm going to say. F decreases stability of N plus. And guys, the same reason F stabilizes a minus is why it destabilizes a plus. Electronegativity pulls electrons toward the fluorine, right? You're pulling electrons away from a cation. What does cation say about that? I'm already missing electrons. I'm a cation. Now you want more? Or use it, say it another way. It's like taking water from a stone. Okay? You've already taken the electrons away, and now you want to take some more away? Hey, they're not there. Okay? So F decreases the stability of N plus. So I'm going to put the 3 before the 2, like you said. And I'm up to 3 more. One is a V is terrible too. How terrible is V? V is really terrible. Do you know why? This is not about aromaticity here, but this LP resonates with furan. If the lone pair is gone, and it will be if you put a proton there, then you've lost that resonance. It's not aromatic resonance, but it's resonance stabilizing that lone pair. It resonates into the ring. Okay? And furan is the ring. I hope you remember that. Furan is the ring. Oops. 1 is still worse than V. That's right, because you're not losing aromaticity with V. You're losing resonance that's not aromatic resonance. It's not as serious. Okay? So V is next. And now we're on to the pyridine. Which pyridine will stabilize the plus charge on nitrogen? And I just want to remind you, nitro is the opposite of stabilizing a plus charge on the other nitrogen. It has a plus charge on the nitro nitrogen. Lone pair on O can resonate and help the nitrogen. Okay? You want to see it? I'm going to put the H here. There's the conjugate acid. You can do this, right? Oops. That stabilizes the plus, doesn't it? So I really like VII, and I don't like VIII as much. So VII would be here, and VII not as much. And you would have to say, I mean, your picture does answer the question. If you left it like this, this is a non-verbal answer that I think is just as good as a verbal. He drew the plus, and he's saying how it got stabilized by this lone pair. I mean, it's there. If you have that picture there, that tells me why. You got it? Okay. I think I got everything I need. I'm going to add something that's not on this question, but it shows up on this question frequently. So this is after the fact. You don't have to copy it. And I know I took you way over time. I'm going to leave it as an assignment for you. I want you to look up guanidine. Guanidine basicity. And if I can remember on Wednesday, we're going to start with that. Look up guanidine basicity. Okay? I gotta change that. It's guanine. Guanine. I don't want your Google search giving the wrong thing. Guanine basis. And that's it for us. Sorry to run over a little.